The harmonic oscillator eigenstates represent our first real view at a set of functions that now have some physical connection, that is, a physical connection to, for example, diatomic vibration. This is different from the particle in a box, which is really a model system that just gives us a sort of qualitative feel for how quantum mechanics works. But let's take a look at the solutions to the harmonic oscillator and see if we can understand a little bit more about what quantum theory implies about molecules. I've drawn here the first few eigenfunctions of the harmonic oscillator, and I've given you the formula again for the eigenfunctions. Note that this is a normalization constant here, so it really doesn't impose any functional dependence on here, but it is multiplied by the Hermite polynomials and by a Gaussian function. And these are the two things that give these wave functions their shape. And now I've written this in terms of this parameter alpha, square root of mu omega over h bar, just because it makes the mathematical form of these equations a little bit simpler. So what can we learn about these wave functions? What do these tell us about quantum systems? Well, I think the first thing I would note is that as we go from the lowest energy state, which is down here at n equals 0, as we go higher in energy, we see an increasing number of nodes. And I'm sort of making spots on the nodes here. So we can see that for this first state we have 0 nodes. For n equals 1 state we have 1 node. For the n equals 2 state we have 2 nodes. And for the n equals 3 state we have 3 nodes. So among the observations that we might make is that the number of nodes is simply equal to the quantum number. All right, but another thing that we can make about this is that for this one-dimensional system, the energy increases as we increase the number of nodes. All right, and this is actually a fairly general conclusion for one-dimensional systems, that as we go higher in energy, we're going to see more and more nodes. And you may recall for the particle in a box, this was also true. So if we drew the first few eigenfunctions of the particle in a box, the lowest eigenfunction had no nodes. The first eigenfunction, the n equals 2 eigenstate, had 1 node here in the middle. The next one had 2 nodes, here and here, and so forth. So as we went higher and higher in energy in the particle in a box, we also saw an increase in the number of nodes. So this is also reflected in the harmonic oscillator, and we would find it's generally true of these one-dimensional systems. Now another thing I would point out is that if we cut this potential right down the middle, and I'm going to try to do this as best I can. If we draw a line right down the middle, the harmonic oscillator potential actually has reflection symmetry across that line. In other words, everything that's over here you would reflect over here. So there's a particular symmetry. So I'll say the potential has bilateral symmetry. Now what does that imply about the eigenfunctions that comes? Well, you notice that the ones that corresponding to, I'll make another note here, for n equals 0, 2, and 4, these also have this bilateral symmetry. So in other words, this line cuts them in half also, and what you see on the left-hand side of the line is the same as what you see on the right-hand side line. It's just reflected across. But when we look at n equals 1, 3, 5, and so forth, they don't have that same symmetry. In fact, what they have at that line is a node, and that's going to be true of all of the odd-numbered eigenfunctions. All right, in effect, what we're seeing is a difference between something that we would call an even function and something that we would call an odd function. And we'll talk about that a little bit more in this lesson. All right, but that symmetry actually has some importance, as we'll see presently. Now, a third thing that I would point out with this is that all of these wave functions go beyond the edge of the potential. So all of the psi sub n extend to plus or minus infinity. In other words, they keep going out here. And if I were to actually draw what we've got here, these lines actually continue on and continue on this way, and these continue on this way and this way. Just didn't have enough room on the computer to draw these all out. But these would all extend off to infinity. Now, what does that tell us? Well, it tells us that this notion that we talked about earlier of classical turning points, remember the turning points were the places where the energy of the system was equal to the potential, and classically you can't go beyond those turning points. But in quantum mechanics, the wave function does. So quantum mechanics is telling us that these particles actually have some probability of being out in this region over here or over here. In other words, outside the area where the classical mechanics would allow the system to be. And this is a very much a quantum mechanical phenomenon. All of these things go well beyond the turning points. You'll notice, though, as we go to higher and higher energies, and this would be even more pronounced if we could show higher energies than this, is that we have a fairly sizable probability of the particle being right near where that turning point is. One way we might interpret this is that near the turning points, the system spends a lot of time because it's moving slower. It's moving slow as it approaches the potential. So in some sort of dynamical sense, the particle is more likely to be found at those turning points or around those turning points than it would be in the middle of the function. All right. So these basic observations tell us something that in fact is quite general about quantum systems. And whenever we have a potential that has this bilateral symmetry, and I should have written the word symmetry out here, it will have this sort of reflection and anti-reflection quality about its eigenfunctions. All of these eigenstates, if the potential doesn't go to infinity as it does for the particle in a box, they will gradually decay as they head out toward infinity. Now, one last thing I'd like to point out, and that is if we were to look at, for example, the average value of the position of a particle in a harmonic oscillator, we would be constructing an integral that would look something like this. We would go from minus infinity to infinity. We would have psi n star of x, psi n of x dx. Okay, but x doesn't have it doesn't change this function like the momentum operator might. So in fact, this is just equal to this. It's just equal to x times the square magnitude of the wave function dx. But if I take the square magnitude of these wave functions, for example, if I take the square magnitude of this n equals 1 wave function, it would flip this part up. So I would have a function that would look like this, that now would have that bilateral symmetry across that central line, which makes it a function that would have the integral just of this wave function squared would have it would be 1. But when I multiply it by x, I flip it again so that it has this uneven symmetry and it has an equal amount of area that's in the negative territory as it does in the positive territory. So because it has this quality, the expectation values, or the average value of the position for all harmonic oscillator states, ends up being 0, because we're basically multiplying what amounts to an odd function by an even function. All right, so the overall integrand in here is something that doesn't have even symmetry. It has odd symmetry. And we'll find, generally speaking, that this average value for a symmetric potential like this is going to end up being 0. This would also be true, by the way, for the particle in a box. If we were to evaluate the average position of the particle in the box, we would find that it would always be at halfway across the box. It would basically always be in the middle of the box.